Okay, hi everyone. I'm going to talk to you about exoplanets, and I'm going to talk a lot about this mission TESS and tell you how, if you are interested, you can actually help find planets or study them too. So in April 2018, this NASA mission, it's an MIT-led NASA mission called TESS, it launched on a Falcon 9 rocket out of Cape Canaveral. And it was an incredible day. It was so clear, and the plume was just so bright. And our whole mission that we had worked on for about 10 years, which isn't necessarily all that long in the field, but it was like up in the tiny, tiny top of that thing, going off into outer space. And TESS takes these incredibly beautiful, spectacular images of the night sky. And I'm going to tell you later how we create time series of star brightness to look for planets around other stars. Now, how many of you, and actually what I am going to try to frame my talk around is trying to answer the key questions that I get asked most often. And these are people by all walks of life. Like literally the type of person you might meet on the subway, bump into at the conference, like kids, other people. And these are the questions. Now, I'm going to ask you to mull over which one you think is the question I get asked most often. And I'll let you know as I go through the questions. So first of all, I was wondering how many of you actually live in New York City? And how many of you have seen a truly dark sky? They're not necessarily mutually exclusive. Well, I think you can still see a few stars from New York City if it weren't for all the tall buildings that get in the way. Actually, I know you can still see a few stars. But the next time you look up at the stars, I want you to wonder what kind of planet might be around that star. Because it looks like all stars have planets. And we have found thousands of planets orbiting other stars. But our Milky Way galaxy alone has hundreds of billions of stars. And so there's probably trillions of planets in our galaxy alone. And so today I'm going to try to give you something to walk away with about what we know about planets and how we're finding them and where we want to go. The first thing we do, of course, is just put them on a plot. And this particular plot it's on a log-log scale, so it's covering an awful lot of ground. And what you can see here on this y-axis, it's the size of the planet in terms of Earth radii. And in astronomy, by the way, we just normalize everything. So Earth is just one Earth radii. It's also one semi-major axis unit. That's the distance from the sun to the Earth. And this is a large fraction of planets we know, and each dot represents a planet around another star. And each color is from a different planet finding technique. So if you could read this plot, you'd see that some planets are over 100 times closer to their star than our Earth is to our sun. And by Kepler's third law, the closer a planet is to the star, the faster it goes around. Some of these planets have a year, the time it takes to go around the star, of less than 1 day. And some of these planets that would be like Earth size, their surfaces would be so hot, they would be covered in liquid lava lakes, not from volcanoes, but just from the heating from the star. You also see at this top end, there are some planets, and by the way, Jupiter, Neptune, Earth are on here. Some planets these crazy planets, hot Jupiters we call them, because they're like Jupiter. Well, they're Jupiter size and mass, but they're so close to the star, and some of them are so big, like double the size of Jupiter, we don't really understand why. It turns out the most common type of planet is a planet of 2 to 3 times the size of Earth, which, by the way, there are no solar system counterparts for. Yet it appears like it's the most common planet, and we don't know how they formed or what they're made of, really, or anything. So there's a lot in this diagram. I wish I could unpack it further for you. But can you guys all hear me okay? Yeah. Okay. But what I do want to say is that, I'd say like 80% or more of exoplanet work is done with Python. Even to make this graph, I just use catalogs, let you access them, or you can download data and use Pandas and just plot things and make cuts. Now, some planet finding techniques don't measure a planet size, and they only find a planet by their mass. And so someone made a program, they call it Forecaster, and it's literally just one line of Python code to convert a planet mass to size, so I can put it on this plot for you. The funny thing, though, is it's based on a probability distribution, because there's no direct relationship between planet mass and size. They seem to come in many sizes and masses, tons of orbits. I hope you see from the plot that it's almost totally full. There are some selection effects and some real features that lead to clumping in this plot. But that was kind of my basic introduction. An exoplanet is a planet that orbits a star other than the sun. We don't know much about planets except that they're there and their masses and sizes and orbits, but I still love to say that in exoplanets, anything is possible within the laws of physics and chemistry. So now I'm going to move on to The second question, when and how will we find another Earth? That's what people want to know. We're nowhere near finding another Earth right now. We're working on it. And just to tell you how hard it is, it's not so much that another Earth would be hard to find. It's not like fainter than the faintest galaxies ever observed by the Hubble Space Telescope. The problem is that on Earth, it's right next to a big, bright, massive star. And the ways to find planets are based on size, mass, or brightness. It turns out our Earth is about 100 times smaller than our sun. Our Earth is about 300,000 times less massive than the sun, and it's 10 billion times fainter than the sun in reflected light. So if you were going to switch gears for a while and look for planets, which technique would you choose? Would you choose one that has to do with planet size? One that has to do with planet mass? Or one that has to do with planet brightness? Okay, it's not really a trick question. I mean, my personal favorite, which I'm not going to have time to get to in this talk, but if you come to the fireside chat, I can talk more about it, actually is the 10 billion one, which is so hard and so hard to do, but it's the future. Now, right now, we're all doing the easiest one, because I think that's what we do as humans. We're doing the easiest thing. And the easiest one is to use planet size. And that's how the large majority of planets are found today. On the top, can you see a planet going in front of its star? That's a cartoon diagram of an Earth going in front of a sun, relative sizes. We don't spatially resolve any star like that other than our own sun. And at the bottom, you see the plot of the planet going in front of the star, and it causes a tiny drop in brightness. And then it finishes going in front of the star, and the star brightness returns to normal. Stars are very, very approximately constant with brightness. That's actually not true, as I'll come to later, but in general. Now, I did cheat a bit because I made it easy for you to pick planet size, but it's really the area ratio that makes the drop in brightness. And so that area ratio, we have to square, right, size and get area. So our area ratio for a true Earth twin is 1 part in 10,000. Now, I know here, except for floating point numbers and stuff, you're not so much worried about precision, probably. Like in engineering, we build things, or if you build a deck at home, or, well, not if you live in New York City, but you're not measuring things to 6 or 7 decimal places or 10, right? You might measure it to 1 or 2 decimal places. So even measuring a star's brightness to 1 part in 10,000 is still really hard. So in exoplanets, we go even further to make our job easier. We're mostly looking for an Earth-sized planet around a very small type of star. There are lots of star types out there, and most stars are small. Not as small as the cartoon I'm showing you. I'm showing you a real image of our sun with some sunspots and with a fake Earth-sized planet. And then the red star is a very, very, very small type of star. It's actually the smallest type of star in this relative size cartoon that can exist. Any smaller, the star would be too cold on the inside, too small, too low pressure to have fusion, which is how we define stars. And I've actually put cut and paste that same fake Earth-sized planet there, and look how much area it takes out, more area. Instead of 1 part in 10,000, like for a sun-sized star, this Earth-sized planet would only take out 1 part in 100 for a small planet. And there's a lot of other reasons why it's very favorable to find planets around small stars, which I don't have time to get into too much of that detail now, but just take my word for it that most of the exoplanet community is kind of racing to find small planets around small stars. Now, one more thing I forgot to mention is not all planets transit their star, because the planet and star system have to be fortuitously aligned so that the planet goes in front of the star as seen from your viewpoint. Imagine if there's a planet oriented like this, so the planet just orbits in the plane of the sky, it will never transit. And so it's just a geometric argument because planets and stars have just randomly oriented stellar axes, and so it's really just a matter of geometry. So yeah. So now I'm going to switch to tell you about the TESS mission and how this MIT-led NASA mission is finding lots of planets. Here's a picture of this mission from a couple of years ago when it was finishing being built. I have the people in this image, they're in a clean room, and that's why they have these so-called bunny suits, because dust and particles from your body and clothes, it's just bad for the telescope. There's solar panels there that will get folded up before launch. There's this antenna that helps us communicate with Earth. Each of these is a camera. They're actually housed in a giant baffle, and the covers are just there. They come off before launch, but they're just there to protect the lens. And each of the TESS lenses, actually you can see in this baffle here, see how it's ribbed? Because stray light from the Earth and Moon, you don't want it, if it bounces inside your baffle, you don't want it then bouncing into the lens. And these ribs help limit the amount of scattered light that hit your actual lens. The actual aperture of these cameras, it's only about this big, 10 centimeters across. And there's 4 identical cameras. And yeah, so that's the TESS mission. I have a couple of like little movies to show you. It's like a beauty shot of TESS in outer space. It's an artist conception animation. It's showing you that the cameras are aligned in a way that they take up, observe a very giant strip of the sky. And this is showing you one camera. It has 4 detectors on it, and it spans 24 degrees, which, and each camera is the same. It's actually huge, huge, huge amount of the sky. And yeah, I'm gonna, okay, let's see. And each of these parts of the sky we look at for about a month, tiling the southern hemisphere night sky, which we've completed already, and then switching to the northern night sky, which comes next. These cameras really look at a lot of stars, about, let's say, millions of stars per month. We can't downlink all our data to Earth, though. Like, if I told you about the memory storage and data rates, you would find it a bit sad for what you do. Like, on board, we store about 200 gigabytes compressed. And when it comes down at about 100 megabytes per second, we have a short window to download data, because TESS is in a very, very highly elliptical orbit about Earth. We downlink the data and uncompress the data, which ends up being maybe closer to, hundreds of gigabytes, several hundred gigabytes to work with. That's how big a TESS camera is. For those of you that are familiar with the constellation Orion, it's like a huge amount of data. And here's a view of our, actually you can't see it, how beautiful it is really, but this is our first sector of data. So each of the 4 cameras, you remember it's taken in a giant strip. They get spread out here, and this is actually satellite galaxies of the Milky Way, the Magellanic Clouds. And there's a lot going on. Like, some stars are so bright, they saturate the detector, and they create a blooming effect. But ultimately, we want to make a time series of brightness of each of these objects. I forgot to mention that. Okay, so our downlink rate it's always low for space. And so we bin data on board the satellite. And 20,000 like choice target stars per month, they get binned to 2-minute cadence. And then the rest of it is the full frame images, like all the data taken. It's only binned to 30-minute intervals, and that's downlinked. So I'm now going to walk you through how we find planets. And what we do is we have to look at a star as it appears on the image. And we want to count up how bright the star is in terms of how it registers on the detector, and do that for the 20,000 points per sector, like per month of data. And this star, by the way, it's not a point source. You know, by the time it goes through the telescope optics, it spreads out over some number of pixels. Because it's such a wide field, stars that get like sent to the edges of the image, they're often distorted in a specific pattern. Bright stars, like this particular one is a bright star, it spreads out, it has this blooming effect where it kind of leaks out a bit. And in this postage stamp of data, we call it, one of the choice 20,000 stars in this particular sector, we will like map out like a box around the brightness of these stars and literally just count that up over and over again for every image. You just sum the brightness up. And it turns out that the pixels, it changes with time, so it's not like uniform each time, because the way that spacecraft might be jittering, sometimes the stars themselves vary, and a lot goes on. So we have to do this for 1 million stars, basically. And here's what happens if you count up that brightness as a function of time. This is showing you time in days, so this spans about 26, 27 days. And this is showing you the brightness of the star relatively, and the units are, I know it seems weird, but it's part per million. So we're looking for small drops in brightness. And this is what we call the raw data. It's not like totally raw, but it's mostly raw. The images would have been calibrated initially. And I don't know if you can see any transits here. There are these drops here. They don't look like the pretty picture I showed you before, because they're compressed in time. A transit lasts a few hours, and on this scale of about a month, they're just all compressed in time. But all of this variation here, it just is partly because of what the spacecraft is doing. It may have to do with the star's activity. We know what some of the effects are, and I'll go over one in a minute. But one of the it's not even like a dirty secret in astronomy, but we will detrend the data often without knowing the physical effects. I know a bunch of talks I heard here, you want to understand the trends in your data, because that's key to your business. Here we don't really, we just want to get rid of the trends. I really wish we could understand all of them. There's one here we do understand, which I'll just tell you, and this was the first, one of the first observations. This is like the first science data, and this is our first exoplanet that the mission found. And the mission operates much more smoothly now, but at the time, where these black lines are, there were known events we call momentum dumping. When a spacecraft is in space, it has to point for exoplanets incredibly precisely. Just like if you, it's not like this, but an analogy is if you take a picture with your camera and it's shaking, like the image is just garbage. And because pixels, like if you could open your phone, look at the detector, shine a laser at it, move that laser across each pixel, and measure the brightness that comes back at you, it actually varies by about 40% across a pixel. And so if that we're varying here, then the brightness we measure back is a problem. So the spacecraft needs to point precisely, but there's a lot of forces moving it around. And there's reaction wheels that move to balance out this motion of the spacecraft. But as those reaction wheels have to keep working more and more and speed faster and faster, something will go wrong if they speed too fast. And so occasionally you have to, it's called momentum dump, you have to de-spin these wheels. And you can fire thrusters to do that, or if you're in low Earth orbit, you can use the magnetic field, but you've got to come and just like, let it go. And that's what happened here. So the jitter would be getting bad and bad things would happen, and here they would dump the momentum, and then it would change a little, and then go back down. That's what those are. These big data gaps here are when TESS was downlinking data. Here there was some kind of jitter problem, so the person who made this, Chelsea Huang at MIT, cut out this data, et cetera. So we detrend the data, and then we get this curve. There's still some noise. It's basically Poisson statistics plus a bunch of other stuff. And here I think you can see the transits. Actually, what she did was she just fit a, I think she fit a spline with knots. So something very simple to just detrend the data. Okay, so now what next we do is take this data and phase fold it, because you can see the repeating pattern of transits, right? And so we'll just phase fold the data and make this what, for this field, is like a beautiful plot. This is a planet. It's got this great light curve where when the planet, this is the flux, the brightness change, and this is time now in hours. So here's the star. It's varying a little. There's some instrument noise. And then the planet crosses over the stellar limb pretty quickly. And now it's fully superimposed on the star, and now it comes back out. So that is the basic way we find planets. And I'm going to get into a little more detail on that. Just in this part where I wanted to say that you can find planets too, I did like a very big picture thing where you can just Google TESS Python, and you come to this page. It's like at NASA, they just keep track of all the different tools you can use to look at planets in the archive. I forgot to say that this TESS mission, by the way, there's no proprietary time, because it's your taxpayer dollars at work that funding the mission. And as soon as the data is ready to go, it gets put on an archive called MAST, and anyone can access the data. So a lot of these tools involve accessing the archive data. There's tutorials on these community tools. There's literally like over 70 things you can download. But just like whatever field you're in, you don't want to just download something blindly. You need to understand what it does. I picked out a really simple example to show you, just because I saw other people put some code up. And so you can see what we do is we rely on like NumPy and Pandas. Matplotlib, of course, is key. And here at the top of this, after we've imported what packages we need, there's the planet URL and this DV URL. That's MAST, where things live. That's where all the data is archived, not just raw data, calibrated data, even the light curves, like the ones I've showed you, you can get those as well. And this simple code, essentially, in here it's hard-coded, but here, there's a planet called WASP-18b, and yeah, you can go down and do a lot of things, like looking in the database. One thing you do is you look for the identifiers, like what else is this planet called? WASP-18b is not a great name, but it's the survey that found the planet, got to name it, but it also has like 10 other names, just from catalogs and other things. And then you can kind of go down and find out the planet mass as encoded in the database, other things about it. And eventually, what's not on here is you can just then pull up the light curves and just look at them, the ones that are made. Now, you might want to analyze your own data. And I picked another easy tool. It's in the form of a Jupyter notebook. But in this one, it's a code called LightCurve with a K. And you could work through it, importing this package, and then searching for one. And I picked the example of the same star I already showed you. It's called Pi Mensae. It's a bright star. In a dark place, you might be able to see it just with your naked eye without a telescope. And here, in this Jupyter notebook, it's actually explaining very clearly, maybe not clearly, but there's a lot of notes about what it's doing. But essentially, remember your key is the set of pixels that the star is lighting up. And so you have this thing called TPF, target pixel file, and you can do various things to it. Like you could find out what its ID is in the test catalog. You can find out which sector it was observed, one, which camera, because there's 4 cameras, that's 4, which of the detectors within that camera. You can choose your own like box around that set of pixels, and you can then like see what numbers are associated with those pixels and kind of relative brightness. And you can make a light curve from it. And they picked this example that just had a very simple way of choosing the aperture. This light curve actually is terrible. Compared to the ones I showed you before, it's the same star. And look, it's like all over the place. Can you see any transits here? Probably not. So then this code is kind of, this Jupyter Notebook is walking you through what you could do. You could choose a better aperture. Here it's trying to choose one. It says TPF create, threshold mask. It's now saying as long as the pixels are above some level of relative brightness, choose those pixels, make your mask, so it chooses a different shape. Looks a lot better now. Here's the part that, if you remember from before, we cut the data out. It's terrible. The spacecraft is jittering like crazy. It's not really usable. Other stuff is happening. And you can just, in one line of code, flatten this light curve, get rid of some points, get rid of some outliers, and eventually you might phase fold the data. And it doesn't look as nice as the other plot, but yeah, there it is. There's your transit. So you could actually, if you wanted to, go to some of these notebooks, download some code. You could fool around because all the data is archived. When I was looking through these to find a good example to show you, I then realized how much jargon there is. And so even though there'd be a lot of jargon, for people in the field, like going to school, studying physics, studying math, doing a bit of astronomy, the barrier to entry is really low now, thanks to Python. It's very low. You can get in the field. You can do data analysis. So I'm going to continue telling you about the planets in a bit of a summary, and then I'll go forward. So our goal is, our steps rather, we want to construct a time series of star brightness for either each star of interest or for all of the stars. We need to detrend the data. Then what we do, what I didn't show you, is we run a search algorithm based on phase-folded data. So we take each stream of data, and we fold it on every phase possible, at every period possible, looking for a signal looking to see if there's a signal in Fourier space. Then after we do that, we can compute some computer-generated metrics to produce a planet candidate list. Our computers sort through all of these planet candidates. We do use machine learning, which I'll talk about in a moment. We use just like algorithms that are more like brute force. And eventually, everything spits out let's say 100 objects or a few hundred objects per sector that humans actually look at to figure out which ones are worthy of being deemed a planet candidate. And we do actually, believe it or not, every Tuesday and Thursday, so that would be about right now, the team meets at MIT between 1 and 3 to look through these planet candidates and see which ones deserve to go out to the community to be followed up with other measurements to see if they're actually planets. Okay, so that's a lot. So I want to show you some of these metrics. Even though I don't have time to explain them in all detail, I thought you might like to see some of them. So for everything that gets flagged as a repeating signal that might be like a transit, this is a summary. Like sometimes there's reports that are like dozens of pages. We have 5-page summary, we have 1-page summary. And here at the top, it's showing you the detrended time series data. So this is in days. And this is, again, relative brightness, but it looks like the units are missing. And here, these blue triangles tell you where the transit is. This panel would be the phase-folded data. This would be zoomed-in of phase-folded data. So that one looks like the plots I've been showing you. We have some other key information, which is the auxiliary data we use to tell whether it's a planet or not. We have a lot of stuff. You'd be amazed with what stars are doing out there. Here's one. It might look like a transit, but in fact, it's an eclipsing binary star. 2 stars are orbiting each other. And this is it looks like there's hardly any noise in this data, but it's just because the signal is so big. It's just very clear. And it has this V shape because as 2 stars eclipse each other, they never cleanly go over the stellar limb. It's sort of like very gradual because you have one big star going in front of another star. It's taking out a different area like at each step. It's never superimposed on the star. We have other things like variable stars. Some of these stars are pulsating, like a heartbeat. They're just unstable. There's one at the bottom that's incredibly pulsating a lot. There's some really pretty things. It's sort of like flipping through a picture book sometimes. In the early days, we looked at all our data. I'm sure it's the same for you, like if you work in industry, like you've got to look at your data and understand it. You don't want to just throw it at a black box computer code. And it was just amazing to see all the gorgeous things that are just happening on this repeated timescale. This one at the bottom is probably some kind of star spots. where the star is changing slowly over a number of days as it rotates. It must have a lot of spots covering the surface. This one is actually a binary star that's orbiting, but it's gravitationally distorting each other because they're so close together, causing like this continuous change in brightness. So I wanted to give a few remarks about artificial intelligence and planet finding, because of course, as soon as you have a big data set, that's what you want to, what you want to do, the tools. We face some unique challenges, but I'm showing you this plot here, which is one of the only 2 planets genuinely found by machine learning in exoplanets. And I want you to look at the y-axis for a moment. So remember, the bottom axis is hours from mid-transit, so the transit lasts about an hour or 2. And that y-axis is drop in brightness. And look how tiny that is. It's incredible. This is a tiny planet. It's about the size of Earth. Oh, remember what I said before? That Earth going in front of the sun would be 1 part in 10,000? This is like pretty much, that looks like close to 1 part in 10,000. And what's interesting here, this was taken not with the mission I've been describing, but another one called Kepler that's now retired. And here, the authors used a deep convolution neural network, and it managed to sift through a ton of data to identify this one as a planet candidate. There's tons and tons of, pretty much I'd say many algorithms you'd be familiar with have been tried for planet finding. We have a few major problems which I want to mention. Mostly, machine learning is used as a classification tool. There's only one case in exoplanets where it has been used to do something you couldn't do any other way. So I don't know for you folks, but I don't know if I feel like happy or sad when sophisticated algorithms are only used to classify. But in the case of this planet on the screen, it had to be, because a lot of the faint targets, there's just too many to sort through brute force or other more conservative traditional methods. There's one case where a planet was found, kind of triggered on, because he's a postdoc at MIT named Jason Dittman. What he did was, it was a ground-based search, and he used weather data taken at the site where the telescope is, and used that as input to the neural network, and was able to decorrelate data based from our atmosphere to find a planet transit. Okay, so most people, your problem is the limited training set. Here for planets, we feel like we have a lot. I said there's like 4,000 known planets. Like, that's not really that many, especially because they're found by a lot of different techniques. In TESS, for example, we've got 30 confirmed planets right now. That's not enough to train on. We need simulated data, which you might want to use. But even in this paper that found the planet I'm showing you, they found out that they could never perfectly simulate a real planet in a light curve, even introducing the planet at the image level. So we're still working on how to make a simulated data set, given that we don't have enough training data. Our next problem is non-uniform labeling. All these beautiful things I showed you before, by the way, we no longer label them. We used to classify and label every one, initially by humans in our first couple months of data, and then we don't even bother, we just throw them out now because we're not interested in them, so we really mislabel data. We right now have an activity where humans are gonna go through like 20,000 light curves and hand label them. But that's our problem too. The other thing is that gaps in the data. I showed you the light curves, there's a lot of gaps. Some algorithms, LSTMs and GANs, they don't like gaps. So we've got to fill those gaps in, and that may skew things as well. Finally, each of these different months, these sectors of strips of the sky, each of them, TESS has different noise properties. So when we train on a certain few months, then we want to find planets in another few months, we kind of run into problems. So yeah, that's where we are. But there's lots of people working on this. We hope we'll make progress. We can always resort to brute force. So right now, as of today, we have almost 1,400 planet candidates from 16 observing sectors. We've got 400 planets smaller than Neptune, 30 published planets. I forgot to give you some numbers. We have millions of stars. We look through, we get, let's say, thousands, 10,000 triggered planet transits, planet-like transits that cross the threshold, and we whittle that down to just dozens of objects. So this is going to end my data analysis portion of the talk, but I wanted to now zoom out and tell you a few other things. Now, what we learn from this is we learn the planet size, because remember, the planet goes in front of the star, and the star drops in brightness by an amount related to the planet-to-star area ratio. So if we know the size of the star, we have the drop in brightness, we get the size of the planet. We know the planet orbit because we see a periodic transit. And by Kepler's law, third law, we also know the distance of the planet from the star. We know something about the star properties already, and so we'll know how very roughly the temperature of the planet, because the light from the star, energy from the star, hits the planet and heats it up. And those are what we know about lots of planets. Sometimes we know the planet mass. It already exists in archive data with a different technique, or we follow it up for that. We also know the planet density, other planets in the same system, but we really want to know a lot more. So I'm going to go back to the question that this part of the talk was supposed to address, which is when will we find another Earth? And so just to remind you, we can't, we're looking for these small planets around small stars on the whole. In tests, we may have like one, maybe, but it takes a long time to follow up these small planet candidates and to confirm them as planets. So I wanted to shift gears slightly and take you on like a virtual trip to a planet orbiting a small star. These small stars are very red. They give off very low energy compared to our sun. And so the planet, if we could go there, if we would go to that planet, the star or the sun might be very big in the sky. Because just like a campfire gives off small fires giving off a tiny amount of energy, you'd have to stand really close to that fire to stay warm. So the planets have to be very close to these small red dwarf stars to have the right temperature. This artist just chose to make the sky red instead of blue and clouds purple. We can actually make some guesses as to what the colors will be, but our data on planet atmospheres is so limited, we can't say for sure. In this case, because I said this like 3 or 4 times already, but the planet close to the star, it goes around much more quickly. And so on planets like this, a year would last just a few days, actually. So you couldn't have this conference every few days. That would just be insane. Maybe they would operate in centuries on that planet. So what's really interesting about the planets close to the star is due to tidal interaction with the star over millions of years, just like we have tides on Earth, the moon we raise tides on the moon. It turns out that the planet ends up in its lowest energy state, which is it rotates 1 time for every time it orbits. It's like 1 day also equals 1 year, which is kind of weird. And our moon, which I know you can see from New York, it always shows the same face to Earth. It actually librates a little, so you get a bit extra, but it's rotating 1 time for every time it orbits the Earth. What this would mean if we can go to the planet is the star or the sun would be in the same place in the sky at all times. So you could choose to go where it's always day, or you might want to go where it's always night, or where the sun is always setting. So on the other hand, visiting this planet might be a terrible idea, because these stars, the red dwarf stars, they actually give off like giant flares. So you couldn't be having your phone all the time, because the high energy rays from these flares would knock out your electronics. If you're worried about UV radiation and stuff, I don't know what it would do to your skin or your cancer-causing, yeah, it may not be good at all. And so we're not really sure. Like on the one hand, remember I asked at the beginning who wants to find planets by their size? Like we're doing the easiest thing, but it may not be the right thing necessarily. We don't really know. And so on our Earth, we had our sun actually also gives off flares. And here's a real image of our sun in just a very narrow wavelength range, so it shows up a little strange looking. And these flares sometimes give off mass. Mass of the sun sometimes comes off. And there was this event in the 1850s called the Carrington event. Have any of you heard of the Carrington event? Okay, great, some of you have. It was, so if you want to have like something to worry about, you can worry about this. Because when this part of our sun came off, by the way, back then astronomers were just studying sunspots. Maxwell's equations that describe electricity and magnetism weren't articulated yet. But a day and a half after this astronomer called Carrington saw sunspots on our sun brighten, our Earth became electrified. It turned out you could see northern lights almost to the equator. There weren't power grid back then, but there were telegraph operators and telegraphs, which when they took the battery out, they operated on their own power. Some of them caught fire. Telegraph lines caught fire. What happened was a small part of the sun had an embedded magnetic field, and it came hurtling towards Earth. It hit our magnetic field and induced a current, essentially. So if that happened today, I think well, not just think, I mean, people do think about this. We would be in big trouble because our entire power grid would probably collapse here. So that's kind of bad news. I just wanted you to know that. I went to a bit of an extreme on this case because when I get asked that question, how will I find another Earth? It's not the actual true Earth twin we're going to be able to look for right now in the next decade, let's say. We're going to fast track by searching small stars for Earth cousins instead of Earth twins. And we're going to use transits, the most favorable planet finding technique for small planets. So that's kind of where things are going in the field right now. And we'll continue on now. Can we go there? so in case you were wondering which question I get asked most often, this is the question, actually. Can we go there? You probably know the answer to it, but here's a picture of our sun. Any guesses as to how big Earth would be compared to this sun? It's, yeah, the size of the sunspot on this. It's actually a real sunspot on this. The next question is how far, away, like if this is the size of our sun, where do you think Earth would be physically located, just for scale? It turns out that just by, again, astronomers, we like to round everything off, but our Earth is about 100 suns away from our sun. So if you take this and like count to 100, so it would probably be like, let's see, I forget what all the rooms are called, but it's somewhere pretty far. And so the next question is, if this was the size of our sun, how far away do you think the next star is? Yeah. I didn't hear what he said, but New Jersey. Okay, yeah, so it's pretty much as far as you could get and still be in the continental US. Far. The stars in kind of this neck of the woods, they're very far apart. And our fastest spacecraft right now, the Voyager's spacecraft are among the fastest, and they are leaving our solar system. They've left our solar system. They're going about 20 kilometers a second, and it would still take them tens of thousands of years to get to our nearest star. So if you just sort of think of those numbers, can we go there? Not for now. Okay, but there's a but that I want to tell you about, because like one of the great things about exoplanets, I mean, we still do all the data analysis, and we do what we call big data for our amount of data. We have data fusion, we do, machine learning, but the line between what is considered mainstream and what is considered crazy is constantly shifting. And this year, the Nobel Prize in Physics went to exoplanets, whereas 20 years ago, even when I started working in the field, it was really fringe. Like people didn't take it seriously, they didn't believe they were planets. And so now, people are thinking about how could we get to the nearest stars. And there's a concept called star shot. And they call it star chip instead of star ship. And the goal here, you can look this up actually, it's by the Breakthrough Organization. The idea is to have these little tiny chips and to launch tens of thousands of them. Just like how in nature, like when the baby turtles are born, there's a lot of them because they're not all gonna make it. And so the idea is to put these little chips up, launch them into low Earth orbit. And by the way, the story gets a bit crazier, but the organization is really good because they list their 19 biggest challenges. So you don't have to, do it for them. And so they're going to go to space and deploy about a 1-meter sail, and then a big bank of telescopes on the ground, very powerful, like 100 gigawatt power overall, will literally shine on these space sails and accelerate them to about 20% the speed of light. That's the goal. And they could get to the nearest star in about 20 years, which isn't too bad. So I thought actually their biggest challenge, I know there's a lot of technical challenges involved, like how not to, evaporate the little sail or the big sail. I actually thought the biggest challenge was getting the land here, because where would you get, what they need is like a square kilometer of land and 100 gigawatt power. Like a 100-watt light bulb, they need 1 billion of those. Because stuff like above it would be, but they actually do. They're in the process of hopefully getting land in, I want to say it's New Zealand or Australia, next to like an old power unit. So it may actually happen. It may actually happen, but I'm just saying that this helps shift that line. So the follow-up question that I'll get is, if we can't go, why look? And I'm getting to the last part of my talk. Well, we actually do what we call remote sensing. We have telescopes like the Hubble Space Telescope. We have an upcoming telescope, it's called the James Webb Space Telescope. There's TESS, by the way. We like to joke that TESS is like the planet finder for the James Webb Space Telescope, which we hope to use to observe exoplanet atmospheres. On the ground now, we're building, or trying to build, the next generation telescopes, like the Giant Magellan Telescope and others. These are 20 meters in diameter, up to 40 meters in diameter. And what we're going to do is study planet atmospheres. So just for a bit of Physics 101, when you think of a rainbow, it's sunlight split up into its colors. But what you might not know about the rainbow is that there are little tiny pieces of color that are missing. And here's a rainbow made by an instrument inside a telescope called a spectrograph. And this is of our sun. And you can see there's little pieces of color missing, where it turns out this is our sun's atmosphere is absorbing. Atoms in our sun's atmosphere, and some of them may be our Earth's atmosphere, are absorbing radiation. So I like to say that the atmosphere takes a bite out of the spectrum. But here, to a stellar spectroscopist, they would know what each of these lines is, what atom it corresponds to, what electron transition. And we actually look at graphs and plots, but I just wanted to show you this one because it's more easily understandable. And you can see how some lines are really thick and dark, Other lines are really narrow and thin, but we try to piece this together based on quantum mechanics of which molecules and atoms observe in which part of the spectrum, and piece together everything that's going on in atmospheres. We're not there yet for exoplanets. We've observed like dozens of atmospheres of hot Jupiter planets, but we need those next generation space telescopes to get down to smaller planet atmospheres. So we do need these spectra, because in the transit method I told you about, by the way, if there's an intelligent civilization looking back at us with a test space mission or something more sophisticated, they can't tell the difference between Venus and Earth. And our planet Venus, it's so hot. It's close to our sun, but it has a giant greenhouse atmosphere. Its surface is so hot. It's like hundreds and hundreds of degrees hotter than our surface. It's hot enough to melt lead on the surface of Venus. So we need to see the atmosphere to evaluate the greenhouse gases and see how hot the planet is. We also want to see gases like water that indicate liquid water oceans needed for all life as we know it. We have gases like oxygen that we all require to live. That oxygen on our planet, it's made by plants and photosynthetic bacteria. But without plants, without life forms that can do photosynthesis, we would have virtually no oxygen in our atmosphere. So we're looking for gases that don't belong. And we actually make complicated models of atmospheres of planets. This is based on like decades of physics and applied physics and Earth's atmosphere. And I don't really have too much to say about it right now. There is a lot of open source Python codes for it, by the way, but the entry level is still really high because you need to know the physics behind atmospheres. And oftentimes, I'm sure this applies for your work as well, but oftentimes you want to just download a code and use it, but it actually doesn't do what you need it to do. It doesn't like reach out in parameter space that you require. So I just have a couple minutes left to talk about, I know I had to leave my favorite project to the end because it was too complicated and new to really articulate. But we want to know in the future when we get exoplanet atmosphere data of small rocky planets, I would hate to miss a sign of life because we didn't know what we were looking for. And so my group, we embarked on this project of trying to evaluate every molecule that can be at gas form at room temperature and pressure, and sort through each of them to figure out if any of them should be on our menu of options of things to look out for or purposely try to look. And this plot is showing you just a bunch of molecules. It's what we call chemical space. Just like space is defined by stars and galaxies, chemical space is the space spanned by all possible molecules. For small organic molecules, there could be like 10 to the 60 of them. For all organic molecules, it would be like 10 to the 200 molecules. I don't think there's any talks on drug discovery here, but there's like a whole field that does this actually. And so in our case, we want to sort through chemical space just in a way that's useful for exoplanet atmospheres and biosignature gases. And we do have a way to filter them. This is like a shaker filter. You're imagining that you have thousands, tens of thousands of molecules. You need to sort them out in some way to find out which are never made by life, which might be made by life and might be useful on an exoplanet. And I want to say that the one thing that made our life so much easier is that there's this open source chemoinformatics software. It's called RDKit. I bet like none of you have heard of it, but it actually, because to describe a molecule, it's sort of kind of complicated because there's a lot of redundancy. There could be a lot of like mix-up unless you can describe it really clearly. And this code has been super useful for trying to sort through these large classes, like all these molecules. So I hope I've convinced you that there's a lot going on in exoplanets, that Python really helps with quite a lot of it. And in many cases, like tremendously lowers the barrier to getting to work on exoplanets. So to summarize, the questions I get asked most often, what is an exoplanet? It's a planet that orbits a star other than the sun. When and how will we find another Earth? I actually, if we find another Earth that has been found by the transit method, you'll not only know how it was found, but you'd actually be able to go and download some tools and if you wanted to, like learn exactly how it was found. We can't find an Earth around the sun right now, so we can't find an Earth around the sun that we're able to follow up and look at its atmosphere. So our fast track is to look for these small planets that transit small stars. Can we go there? Not for now. But I want to tell you that in exoplanets, like the seed is planted for the future of trying to figure out how we might get there. And if we can't go there, why look? Because we can use sophisticated telescopes for remote sensing to search for water and signs of life in small, rocky, temperate planets. Thank you for your attention.